Hello everyone and welcome to this video. In the previous videos, you have been introduced to the concept of the individual decision maker who, faced with their choice set of feasible discrete alternative, is going to select the one with the highest utility. For many different reasons, we have explained you that this utility is best viewed as a random variable. In today's video, we're going to be interested in the special case where the choice set contains only two alternatives. You may think about alternative I as the decision to take the car to go to work, as alternative J as the decision to take the train, for example. And the goal of this video will be to derive an operational binary choice model. Why binary? Because the choice set contains only two alternatives. You may be wondering why we start with a choice set with only two alternatives. The reason is very simple, is that it is a very simple case, so we can introduce many ideas and concepts very easily, but many of those ideas and concepts will remain valid when we will extend the analysis to choice set containing multiple alternatives. So today we are interested in special case where the choice set Cn contains only two alternatives, I and j. Each alternative has an utility uin and ujn, and this utility is composed of two main terms. The first term vin, vjn, is the deterministic part and represents everything that can be observed by the analyst, while the second term epsilon in, epsilon jn, is everything that cannot be observed by the analyst, plus any measurements or specification errors. The choice model is then the probability P and I that individual n is going to select alternative I, and is the probability that this alternative I creates a greater utility than j. Substituting the utility expression above in this expression, I have this, and if I rearrange the term, I have this. Finally, if I decide to call epsilon n the difference between epsilon jn and epsilon in, I have that the probability for individual n to choose alternative I is simply the probability that epsilon n is less or equal than vin minus vjn. What is very important to notice here is that only difference of deterministic utilities does matter for the choice set. An important component of any operational choice model is the error term. And now we're going to see what are the assumptions that are made about those random variables epsilon in and epsilon jn. And we're going to try to answer three questions. First, it's what they mean, then what's their variance, and finally what's their distribution. We note here that for the binary situation, it would be sufficient to make assumption about the difference between the error terms, epsilon n. But because we would like to generalize later on, and we would like to create a story that is easily extended to the more general case of multiple alternatives within a choice set, we're going to do assumption on each epsilon variable, epsilon in and epsilon jn. So the mean. Let's assume that the mean of epsilon in is beta in and the mean of epsilon jn is beta jn. It could be any value. Then an interesting property is that I can always define the new epsilon variable, epsilon prime, as the difference between the previous error term, epsilon in, minus the mean of epsilon in, beta in. And doing so, I can obtain a new epsilon variable, epsilon prime in, with a mean equal to 0. Doing so doesn't affect the choice probability, as you can see here. This probability is completely equivalent to this one, which is also equivalent to this one, and is completely equivalent to this one. And again, we use the same trick. We define the new epsilon prime n variable, which is the difference between epsilon prime jn and epsilon prime in. So, in definitive, what we can see is that the mean of each error term can be moved to the deterministic part. And this mean will be captured by a parameter and will be estimated from the data. This mean is called the alternative specific constant. And the very important thing to remember is that only the mean of the difference of the error term, so epsilon n, is identified. An interesting property of the choice model is that the choice model is not affected by a uniform shift of all utility functions. So it means that I can decide to add or to remove a constant k from the utility of each alternative, so I and j in this case, and this doesn't affect the choice probability. So as shown before, it means that the utility in and utility jn can be expressed as follows. So we removed the mean of the epsilon error term variable from the random term to the deterministic part. But this specification is also completely equivalent to this one, which consists to add the difference between the mean only to the utility of the j variables. And it's also completely equivalent to this one, which is to add the difference between the mean to the utility I. All those specifications are completely equivalent, and in practice what is generally done is to normalize one constant to 0 and to estimate beta n, that is the difference between beta gn and beta in. Another interesting property is that the choice model is not affected by a uniform scaling of all utility functions. And so what you can see here is that I can decide to multiply each utility by a constant alpha without affecting the choice model. So what about the variance? As you can see here, the issue is that the variance is not identified. Any alpha can be selected arbitrarily, and so any variance can be assumed. It also means that there is no way to identify the variance of the error terms from data. And so the scale has to be arbitrarily decided. In practice, what is done for convenience is to normalize the scale parameter to 1. Finally, what's the assumptions regarding the distribution of those error terms? The assumption made here is that epsilon in and epsilon jn are the maximum of many random variables that capture everything that cannot be observed by the analyst. So it can be things that I cannot observe, such as mood, experience, but it also measurements and specifications errors. Note that assuming that epsilon in and epsilon jn are the maximum of many random variables is somehow consistent with the maximum utility theory. Since we are interested in the alternative that is going to generate the highest utility, it makes sense to be interested in the maximum of all those unobservable attributes. From statistics, we know that the maximum of many identically and independently distributed random variables approximately follows an extreme value distribution with location parameter eta and scale parameter mu. Then, from statistical textbooks, we can retrieve the probability density function of the extreme value distribution, which is expressed as follows. And we can also retrieve the cumulative distribution function, CDF, which takes this form. Which is very interesting here is that this cumulative distribution function takes a closed form. This is a very nice property that's going to be very useful later. So here you can see the probability density function of the extreme value distribution. And you can see that unlike the normal distribution, the distribution is not symmetric. So you can see that it is skew and it has a bigger right tail. And it makes sense as the probability of highest value is higher as we're taking the maximum of those values. And here you can see the cumulative distribution function. Again, from statistical textbooks, we can retrieve the properties of the extreme value distribution. So here are the mean and the variance of epsilon if epsilon follows an extreme value distribution. And gamma is simply the Euler constant. So now what are the assumptions on epsilon in and epsilon jn? Is that epsilon in and epsilon jn's are following an IID extreme value distribution. And remember that if we include an alternative specific constant in our model, then it means that the mean can be assumed to be any constant. And in practice, it's convenient to set the location parameter to 0 so that the mean of the error terms is gamma over mu. So now we have the distribution of epsilon in and the distribution of epsilon jn. They both follow an extreme value distribution with location parameter equal to 0 and mu as a scale parameter. The problem is that what we need is the distribution of epsilon n, that is the difference between epsilon jn and epsilon in. Unlike the normal distribution, the difference between two extreme value distribution does not follow an extreme value distribution. But again, from statistical textbook, we know that the difference between two extreme value distributed variables follows a logistic distribution. And the location parameter is 0 and the scale parameter is mu. Again, if we go and check our statistical textbook, we will retrieve the probability density function of the logistic. And again, the very good news for us is that this cumulative distribution function has a closed form, as you can see here. And so finally, it becomes easy to derive the operational binary choice model. So the probability P and I that individual n is going to select alternative I is the probability that this epsilon n is less or equal than VIN minus VJN. So now that we know that the epsilon n follows a logistic distribution and that we know the cumulative distribution function for epsilon n, it becomes trivial to compute the binary logit model, that is the probability P and I that individual n is going to select alternative I. And as you can see, it's a closed form expression that is a function of VIN and VJN. I hope that you have enjoyed the videos and that you have understood how to derive an operational binary logit model. In the rest of the week, you're gonna learn how to estimate those models. But first, I invite you to test yourself by doing the exercises that are proposed.